Hi guys, I'm back. This is kind of a video I want to do to just kind of answer something about on a comment, and it's basically, I figure if one person's asking, then there's probably several others that would be interested in this, hopefully, and I'm hoping I can understand the question right. So I'm going to kind of go around this a little bit, go probably a little more deeper in what maybe they wanted. But it was basically about testing a network of parts or the circuit and stuff, and what, basically what you can test, what you can't test, how can you test it, or can you test it, stuff in circuit and stuff. So we're going to go from this from a standpoint of first that you've gotten something to work on. It just arrived in a box, shipped to you. It can be a radio like this here. It can be here's just really be the only circuit I'm going to talk about, because that's all I got is the chassis for is an amplifier, goes with a phonograph, or it can be any other type of receiver. It could be a TV, it could be, or it can be a piece of test equipment. So first and foremost, let's talk about, you just got it, so and maybe you want to test some stuff. Well, right off the bat, the first thing I want to tell you is, as far as capacitors go, the only way really truly to test them, especially for leakage, but even really get a good read for capacitance, is with them out of the circuit. I know there are some testers that were built to check capacitance only in circuit. And they're reasonably accurate at that for the most part, but you can't test leakage with them in circuit. So as far as your paper caps, your electrolytic caps, such as these guys, and then of course any of these capacitors like the 0.005, the 0.02, and so forth, those they need to lift one end. You don't have to pull them clear out, but at least lift one leg to test them. So I wanted to get that out of the way first. Now, as far as resistors, now in the representation I got here of the two things I got here, pretty much every resistor in here can be tested in circuit. There's not really anything that's in parallel with them that can cause a not a good read or not an accurate read. So for the most part, about the closest things would be, if you wanted to say that you may have a little troubles, is the cathode resistor on this tube, and also feeds the other tube, because it's got a 20 microfarad cap across it. Now a capacitor blocks DC, but it has to charge up to do so, and a 20 microfarad, you can still read that resistor, but you're gonna have to wait a few seconds, as you'll notice your meter start out low and slowly climb. It'll take a few seconds depending on how much, how good the battery is, what kind of battery you're using. It's a 9 volt or 1.5 volt and so forth, how long it takes to charge that. But eventually it will get fully charged, and then you'll be able to read the full resistor. But if you do feel that you would like it, or feel like that's not accurate, you can break this top end right here. You can't really break the ground because that's actually was in a can, so you'd have to pull the can to do it, which in case you would actually break this in anyway. But otherwise you could check it. But as far as pretty much the rest of the resistors, except for some cathode resistors that have bypasses on them, this radio don't have a bypass, but pretty much all the rest of them are not in parallel with anything. And as long as there's a few blocking caps, coupling caps and things of this nature, as long as they're good, they're not leaky, then the resistors should read without any problems. Now, and of course, the nice thing about a SAMS, it gives you a resistance chart. So that's basically measured from the pins to ground. In fact, this one is, everything is to ground. Now sometimes you'll read these where it tells you it may be to another point. It'll be a little note. So make sure you read through the entire directions on it and everything. But otherwise, but this radio here, excuse me, this radio here is, everything is from the pins to ground. And you can just check all the resistances and see if they match up within plus or minus 10 to 20%. Okay, now one thing I wanted to talk about, though, and it kind of brings back to this question. Let's look at the radio first. And let me kind of zoom in maybe just a little bit. So it's a little bigger. Hopefully it's decent size for you. I want to keep the whole schematic here for a moment anyway. For a newbie, someone that's new in this, and you know, we all were new at one time. You know, you see, you know, a bunch of symbols on here, and you know, it looks kind of complex and everything. I want to show you how to break it down, because there's actually several circuits in here, and each circuit really is self-contained. All the circuit before it does is give it an amplified signal, gives it the signal, and then it takes it and amplifies it or does something to it and then sends it on to the next circuit, the next stage. So I want to show you how to break these down. Now, let me see here. Trying to find the easiest way here. Okay. Let's look, we'll go from the front end to the output. Okay. So here we are in this front end section here. Now don't really concern yourself about the switches. We're more interested just in this general circuit, this RF right here. So what is part of that circuit? Well, on the grid side of the circuit, the input side, it comes from here and down. It's this antenna circuit. That makes up the grid to this, or the input to that grid. And it basically is also going to be the grid return or grid load. So it's part of this stage. So your antenna coil, the loops, and all that is part of that RF tube. And that takes care of the grid, the input. On the output, basically everything from this coupling cap back is part of that circuit. So I could actually take and break the circuit right here. So everything else is gone. And probably the easiest way to do this would be, you get a piece of paper here. So, right there. So, except for, don't worry about the switches so much, because that's just switching whether it's AM or you know, the broadcast band or shortwave. But that's this circuit right here. That's all there is to it. So basically all you got is, you got this peaking coil. Don't get too concerned about what it does or exactly how it works. That is going to be a much later video down the road. But then we've got a couple resistors here that are hooked on the B+ line. This line here is the power supply from the power supply. Comes clear back here, connects here, and down through the filters, up through and back. So this is supplying our B+. We have a resistor here and a resistor here. These two combined make up for the load for the plate, and actually the primary is this 1200 ohm. So all that's doing is setting the proper B plus and the proper load for this tube for for the application that it's going to be doing. And then on the grid side, the primary thing is really this antenna coil, and the secondary of it, it sets up the bias for the grid. So that is your circuits for that circuit. That's all there is to it. Not much. You've got a cap here, which is tied off the cathode. It's a cathode bleed cap. You've got your heater circuit, you know, and also the cathode goes to ground here. And we've got our grid circuit, which is basically this antenna coil, and that's it. The plate circuit, which is these two resistors, and that's all there is to it. From that point, what it's going to do through this coupling is feed its amplified signal to the next circuit. Now there's actually two circuits here. We have a mixer tube, the mixer part of the circuit that's going to mix the signal, and then we've got the oscillator, which is down here. So really, all this is going to be is getting our piece of paper. That's what I'm doing. So in this, we've got the coupler, and right there is our output. But we actually have two circuits in one. We have the oscillator down here, which is working between this grid, the cathode, and this grid. And then we've got the input signal, which is coming in on this grid, and its output is the plate here of the mixed signal coming here. So the oscillator part, it just makes up of these coils and feeding into here, so to operate the oscillator. The input signal coming from the RF is coming into this grid. This and this signal mixes inside. I've talked about this before. And then we feed it and amplify it and feed it out the plate, which is loaded down by the primary on the first IF transformer. The B plus comes through these coils and feeds up and comes through the primary to the plate. So again, not really a whole heck of a lot to the circuit. In fact, this is the most complex one because there's actually two circuits in one stage here. Now some radios will have a separate oscillator tube, but most of them you'll find they're using one tube, doing both the mixing or converting and the operating the local oscillator. Once we leave that, of course, the only thing the IF transformer is going to do, and it starts with the first stage here, and really it's just the primary stage, is it's a bandpass filter. It's only going to let through one frequency, and in the case of this is 455. So that is taken care of really right here. But we do have another tuned circuit here that's tuned to 455 as the secondary. That ends up being part of the grid of the IF tube. And the plate of the IF tube is on this primary. And that's all there is to that circuit. Real simple. This loads the grid, gets the bias just right, plus it's picking up an AVC voltage that is a preset voltage. When there's no signal at all, will be predetermined by the diodes on the diode detector tube, and that sets a preset voltage. And then if the stronger the signal is, the greater this voltage will be. And the less amplification you get here, the weaker the signal, the less this voltage is, and the stronger the signal gets through. Again, this will pass through that 455, get filtered again, and then we run into our next circuit. Another little setup where we have a tube doing three different things. So this is just a 12SQ7. It's just a dual diode and a triode amplifier tube. So there's two diode plates and then just a standard triode unit in it. So you got the two plates here, and one's here and one's here. One just goes to ground, so they're basically not even using it. The other one is the only one that they're using, which will double play both as a detector and also developing the AVC voltage. The other part of the tube consists of a plate and a grid, and the cathode's common to everybody here. So in the plate, we go over to this point here. This is our load resistor for the plate, which supplies the B+. It's hooked off the same B+ line, goes through that resistor and sets our voltage here. Cathode to ground. Grid comes down here. It is self-biased with this 4.7 meg resistor here. They're using this, and it uses a particular type of biasing known as contact bias, because this resistor is fairly large. So this is the grid resistor, this is the load resistor for the plate. That's all there is to that triode circuit. As far as the diode circuit, you just basically got the one diode and the cathode going to ground, so the signal just feeds through and feeds back through the volume control to ground and back up. And that's all there is to that circuit. The last circuit basically is our output tube. We've got a coupling cap, and we get the signal from there, feeds into, develops across this load resistor here of the grid, also known as grid leak resistor, but really the proper name is load, because grid leak entails that we're self-biasing by a grid leak method. This is self-biasing though by the cathode resistor. What this resistor does is just sets the cathode and pulls it to a positive voltage with respect to the grid. Well, if you flip that around, then that means the grid is negative with respect to the cathode. So depending on the current going through here, 120 ohms will be what the grid is actually biased at. So this thing is just a place to develop the voltage across. That's basically what all the grid resistors do, is something to create a voltage drop across, so then I can feed that into the tube. We come out amplified on the plate, and the transformer, the audio output transformer, mainly the primary coil, sets up an impedance. There's a impedance here that makes up my load that I need for this audio output tube. And that's where my signal gets developed, feeds through, and of course then feeds the speaker. All the rest of the circuit is just the power supply, which entails just a half-wave rectifier, a couple filter caps, made up through a pi filter with the 1200 ohm resistor here, and a little bit of the primary coil here. to reduce hum. Now, if we take any one of these circuits, we can diagnose any problems with that circuit by just making some measurements. The very first thing in any type of diagnosis or troubleshooting is your voltages. So you want to follow your voltage chart. Pretty much all schematics, and I went over this a little bit the last time, but you'll generally have at least some voltages. And generally the ones that you may have, do have, will be at least maybe a potential B plus line voltage and a few plate voltages. The better the schematic, the more voltages you got. But you check voltages. Make sure your voltages are within a reasonable amount. Again, like I said in the last time, depending on the meter you use, how much input you're putting in, you know, what did you plug it into and stuff, will determine how far off that voltage may be. Because it may be off, it may be a little high because of the meter you're using, or if you're plugged in something that's more than 117 volts in this case. But in any case, read your voltages. If anything is more than 20% out, definitely more than 20% out, then that is the circuit you need, or the part of the circuit that you need to check out. So if the plate was off, let's say the plate voltage here is way high. Well, you know, it's basically B plus. And of course this is a poor example because it really is B plus. But let's just say that it was pretty darn high. Then the likely cause of that is we're not loading down across here. We're not getting no drop. The only way we're not getting any drop across the load is we're just not flowing current. If we're not flowing current, that means the tube is not conducting. Tube not conducting would tell us that the grid is way negative. It's cutting the tube off. So really where the problem is would be back in here. More likely what you're going to find on an audio output tube is that the tube's getting warm and this plate voltage is low. Now the reason why it would be low is because it's really pumping a lot of current through. A lot of current's going through the tube, and that's why it's getting really hotter than it should. You know, the type of situation where if you turn the lights off, you see the plates on the tube getting red. In a case like that, that means the tube is conducting too much, which means the grid is not negative enough, or may even be positive. And most likely it is because this capacitor is leaky. What this capacitor hooked to on this side? B plus. This is a positive voltage here. So if this becomes leaky, I start putting a positive voltage on the grid, which is a no-no in this particular tube, or in any audio, most audio output tubes. So once I start putting B plus on here, or some positive voltage, this tube goes to maximum. It goes to saturation. And that will drop more voltage across the load, which means then I will have a much lower plate voltage than I should have. But so check your voltages and try to understand what's going on in the tube. Tubes are reasonably simple. They basically, everything is related to the cathode, and most of these sets, except for this one, most of these, the cathodes go to ground, so the actual voltages you're measuring is to the cathode. This one's the only one that isn't, but everything's related to the cathode. The cathode produces our electrons, so that's where the current's coming from. The grid, the control grid, is just that. It's a control. And since electrons are negative, the more negative the grid is, the more it blocks those electrons getting through the tube, which means less current going through the tube. Less current means less voltage drop on any one of these loads that's in the plate, whether it's a resistor or a coil with impedance, doesn't matter. It is not going, if there's not as much current there, you're not going to, Ohm's law just tells you you're not going to get as much voltage drop across it, so the plate's going to read higher. If the tube is not, if the grid's not very negative, then more current flows, more voltage drop across the load, higher, the lower the plate voltage. So, if we just isolate it like this, then we can start looking at the individual parts of the circuit. Not much to the grid. You just got a resistor that goes to ground, and you got this coupling cap hooked to it. So basically, if you got a problem with this grid, you find that you do like a positive voltage there, then most likely it's this cap being leaky. If you're getting absolutely nothing there, zero, check the resistance on this resistor. It could be shorted. There's times when the resistor's open. When that happens, you may still not read anything on here, but if you was to measure the AC or actually use a scope on it, you would see that you'd get a signal there, but it's bouncing. It's just kind of floating. It's not quite right, and the output will be detrimentally off because the grid literally floats. If the grid is way negative, more than it should be, then most likely in this particular circuit it's because this resistor is high. If this drifts, the higher this drifts, the more voltage drop has crossed it. More voltage drop across means more positive voltage at the cathode, which means that this grid then, respect to the cathode, because everything is respect to it, the grid will be higher negative. So basically, this is how you test stuff in circuit. Is mainly you're looking at voltage more than anything else, and you're determining by understanding how the tube works and the circuit works, and more or less really the tube theory. So go back over some of my tube theory videos if you have questions about it. But understanding how the tube works will let you know how them voltages can vary. Now, I'm going to throw one at you. Let's look at this guy, this amplifier, which I've started working on. Let me put some light on this. I'm sorry about that. It probably was a little getting dim in here. See how this works too. Okay. Now, let me get this rotated around. Let me zoom in just a little bit more. There's two circuits through here because it's a stereo amplifier, so it's got a left and a right, but they're just identical. They're clones of each other, so we're just going to look at one. So I can zoom in a little more. The rest of this, like up through here and through here, is the radio tuner, which this unit did not have. It's just the phonograph with the amplifier. Let me zoom down just a little bit more. Alright, let me see here. Alright. So, let me move it over. I'll give you a quick run through how the signal goes through it. Since I don't have a tuner, it don't pick up tuner, and I don't have a tape, so I'm not hooked up to those inputs. The only thing that's hooked up is the phono input. Goes through a switch so that you can switch which inputs you want. That feeds into a preamp, triode preamp, which in turn feeds out. We have bass and treble here, controls, and then they feed to the volume control, which then feeds to the first audio amp, then to a second audio amp, and then the output audio amp. So I want to zoom in on that output section, or the amp right before it. Now I've been going through this thing, like I said, I've started work on it, and the one thing, of course, I'm replacing all the paper caps, so I'm just clipping as I go along. But I wanted to check some resistors, and I've found some that were a little bit out of tolerance, mainly the high wattage ones, the high current ones that was in the bleeder network down here in the power supply. Some of these are a little bit off, and so I'll be replacing those. But I get to this resistor. Let me use something else better. Right here. Now there's an identical tube. Like I said, there's left and right, and they're just clones. So there's an identical circuit right above it, right up here. They both have 100K ohm resistors feeding for a plate load, feeding the plate on the tube. Both these resistors are open. They measure infinity. Now the interesting thing is, I operated this thing. I actually put a record on it, and it played. It had a lot of hum. The filter caps were definitely bad. So she had a good amount of hum on it and stuff, but it still outputted a signal. This resistor's open. I'm not getting no B pluses plates. That effectively kills that tube. How in the world was the signal coming in this way, coming from the phonograph, getting to the output and out to the speakers? Now you can pause the video here and think about it if you want. Don't start typing any comments, because I'm going to tell you how it got there. And it's a unique thing about tubes. First of all, tubes have interelectrocapacitance. So these are triodes. If they'd been pentodes, it probably wouldn't have done it, or at least it would have been a lot worse. And you know, I was just doing a simple test. I knew that he had the thing on when I got there. He had it plugged in and turned on. So I knew that it came on. And he had he was inputting in the tape input a signal in there, and you could hear something coming out of the speakers. So I knew it worked. So when I got home with it, my curiosity got to me, and I went ahead and just plugged it in and fired it up. I wanted to check and see how well, or if the phonograph worked, how well it worked and everything, if the cartridge is good or anything. So, and it, you know, I played a record and I got music out. Now, like I said, it had a hum, and the hum would reduce the signal some, and plus also knowing that you know, a lot of paper caps in here, some of those could probably be pretty leaky, and that would reduce the strength of the signal. And if the cartridge is getting weak, it would have a low reduction in the signal too. So I wasn't really concerned about, you know, how loud can it get or anything like that. Plus the volume control is extremely dirty, real scratchy. So, but how did it work? Well, we have a triode tube. It has about 4 picofarads capacitance between the grid and the plate. Now, that's not a lot of capacitance, and if you actually operate the math out on it, that works about 7 megs of capacitive reactance, or AC resistance, as far as the capaciting circuit goes, of getting through here. Now that seems like a lot, and it, under normal circumstances it would be, but we got to look at what we're doing here. We have this nice Pinto tube here, 6BQ5 audio output tube. This puppy has got a pretty decent, it's somewhere around about 10 to 15 megs in that range of input impedance. Real high input impedance on that grid. So it's, you know, it doesn't take much to get it to much signal to get it excited, because it don't take much current at all. It don't need much because it's a pretty high input impedance here, and it's actually higher than what this resistance is here, AC resistance, capacitive reactance. So, and if this tube, the one before it, is operating pretty good and sound, in other words, I'm getting a pretty good amplification here and proper amplification feeding through, and it's resistor test right on the money, then that signal goes through here. It's just as though this tube's just not here. It's like it's connected from here to here, because this impedance is higher than this here. So it just passes right through there because of the capacitance inside the tube. And it's not going to down it too much because this tube's not asking much current. The only way I can get a decent voltage drop on that 7 megs is if I'm drawing some decent current through it. If this tube is not asking for much current, very little current, then I'm not going to get much voltage drop across that 7 megs. And not much voltage drop, then the signal just passes right through and without any real problem. Only thing that's not happening is it's just not getting amplified like it was designed to be. So that's how it was able to get through. And that brings up something that I know some of you who've watched videos on YouTube now for a while and seen different people doing different things, working on different stuff, and they may be, you know, operating the stuff and then decide to test the tubes and find the tubes weak, bad, have leakage, things like that. They replace those tubes and it don't really show much change. Well, the reason is right here. That's part of the reason. The other part of the reason that you won't see much change sometimes is even with an audio output tube. If you're not running that thing at full max input into it, trying to get the maximum output out of it, in other words, crank that thing up full volume and run it all the time or testing it that way, that tube could be weak. And if you're, you know, the max you ever run is like quarter volume or something, then about the only thing you might notice by changing it out with a new tube is now it's more like quarter volume, where before you had to crank it maybe to half volume. But unless you're pushing an amplifier to its maximum, anything wrong with the tubes, you're not going to notice much difference by putting new tubes in until you actually are trying to compare it at both maximum levels of signal in both situations. Because as long as the tube's trying to do something, or as long as there's a pathway through there, and there's enough different levels of amplification, such as this, then the thing will seem to work just fine. And that's what happened here. Now, if my input coming off of the phono was right directly to this tube, then it wouldn't have worked. But the fact that I've got a tube here, amplifier, and I've got a preamp before it, we've already amplified that signal pretty darn good. And the fact that we were then directly feeding into this audio output or power tube that is a pentode, which tells us it has a pretty darn decent input impedance. Then with a strong amplified signal already, high input impedance, then the signal got through without any problems. Now, granted, fixing those resistors will definitely improve it, because then I'll get that next stage of amplification, and these tubes will then be amplifying. But if I'm not running it very loud, I wouldn't have never noticed anything. And as it was, I didn't notice much. I was more paying attention to the fact that I got hum, and my filter caps are bad, and knowing that a lot of other stuff could be bad in here, such as a lot of leaky paper caps. Anything that I might have even suspected about being a little weak on output, I just automatically pushed off onto those things. And they are at fault too, but so was them bad open resistors. So I hope this kind of answers some questions. I hope I answered that one question, at least somewhat anyway. And I'm not sure what I'm going to call this. Maybe answer to comments or something. I don't know. But if you have any other questions when it comes to, schematics, circuits, and stuff, then we can start breaking this down even more and go a little more in depth. But otherwise, any other questions, just ask, and I'll see what I can do about making a video on it. So anyway, now that I've got past this point, the next couple videos we're going to be talking, we're going to finish up on inductors real quick. There's not much left to talk about them, or coils and stuff. Basically mutual inductance, and that's about it. And inductors in series and parallel. And then we're going to feed right into our filtering circuits in AC. And what we'll be talking about, start off with, is we're going to be talking about bandpass filters, tank circuits, and the like, and series circuits. And I'm going to explain to you why this side, the primary side, is a tank circuit. Parallel capacitor and coil, it's a tank resonant circuit. But the secondary is a series resonant circuit. Now I'm going to tell you why it is. But use the same formula though. Resonance formula. But we'll go into why this side is series, or this side is parallel. Even though it's drawn the way it is, it still acts as a series resonant circuit. So be looking forward to that. I should be getting started in that on the next video. So I want to thank you for all your comments and my new subscribers. If you like these kind of videos, you just stumbled across this one, and you like videos like this, and you like, also I do work on radios and stuff, and I tried doing some series on those when I'm not doing this stuff here. If you like all that kind of stuff and you haven't subscribed, please subscribe. That way you'll know when my next videos are out and stuff. If you like this particular video, give it a big thumbs up. And so I think that's about it. If you have any questions, just ask and we'll see what we can do to answer them. And thanks again for watching. I'll see you guys on the next video.